lecture is going to talk about hypotheses, significance testing, and confidence intervals. Hypotheses are a central component of any scientific study. The different types of hypotheses include null and alternative, and these types help form a plan for answering the questions asked by the purpose of our research. The null hypothesis provides a starting point and benchmark for research, and we use it as a comparison as we evaluate the acceptability of the alternative hypothesis. So what is a hypothesis? It is an educated guess whose role is to reflect the general problem statement or question that's kind of motivating that research. It helps us translate that problem or question into a form that can be actually tested. The null hypothesis is the starting point. It is what is accepted as true without having more information. In the top, you'll see that the symbol for a null hypothesis is a capital H with a sub-zero. This is the benchmark to compare our outcomes to, and it proposes that the hypothesized change, difference, or relationship truly doesn't exist. So in an example of a football coin toss with 12 games, the null hypothesis would be that our mean for the number of times the coin landed heads would be 6. So the null hypothesis is that there's some other examples I have here. There will be no difference between the average score of the 9th graders and the average score of the 12th graders on a memory test. Another example, there's no difference between the effectiveness of community-based long-term care and the effectiveness of in-home long-term care in promoting the social activity of older adults when measured using the Margolis scale of social activities. Another example, there's no relationship between reaction time and problem-solving ability. And finally, there's no difference between Caucasian and African American families in the amount of assistance families offer their children in regards to school-related activities. The alternative hypothesis is denoted as a capital H sub 1 or H sub A. And this is a statement that there is a relationship between two variables. They're usually statements of inequality, and it proposes that the hypothesized change, difference, or relationship does exist. In the coin toss example, we would say the mean is not equal to 6. So some of these examples, similar to the null hypothesis, these are the alternative hypotheses. The average score of 9th graders is different from the average score of 12th graders on the memory test. The effectiveness of community-based long-term care is different from the effectiveness of in-home long-term care in promoting the social activity of older adults. Slower reaction time and problem-solving ability are positive related, and there is a difference between Caucasian and African American families in the amount of assistance offered to children in school-related activities. So these are all statements of inequality, and they pose some sort of a question between variables, and they're not equal, as in the null hypothesis. A non-directional alternative hypothesis shows that there is a difference, but there isn't a direction specified. So here is an example of H sub 1, where x1 is not equal to x2. So some of those examples, the average score of 9th graders is different from the average score of 12th graders on a memory test, because the direction of the difference between these groups is not specified. So the hypothesis is a research hypothesis or alternative hypothesis because it states that there is a difference, but it's non-directional because it says nothing about the direction of that difference. This could also be represented similarly to what's presented on the slide as h sub 1, x sub 9 is not equal to x sub 12, where h sub 1 represents the symbol for the first research hypothesis, x sub 9 represents the average memory score for the sample of 9th graders, and x sub 12 represents the average memory score for the sample of 12th graders. Now, a directional alternative hypothesis reflects a difference, but the direction is specified. So in this example, we have A is greater than B, or B is greater than A. In our example with the 9th and 12th graders, we may say that 12th graders have a higher memory have a higher score on the memory test than 9th graders. That would be a directional alternative hypothesis. And you would want to use a one-tailed test in these situations. For the non-directional, you would use a two-tailed test. Here are some examples of null, non-directional, and directional hypotheses. These are all the same ones that I've been talking through on some of the slides. I just want to point out that this says research hypothesis, and that's referring to the same thing as I'm saying as alternative hypothesis. So a research hypothesis and alternative hypothesis in this situation are meaning the same thing. Some differences between the null and alternative. A null has no relationship between the variables, or that they're equal or they're equivalent, and alternative has some sort of relationship. The null hypothesis is indirectly tested while we test the alternative hypothesis directly. And the alternative hypothesis is explicit in testing something, and the implied is null. What are some things that make a good hypothesis? First, it should be stated in declarative form and not as a question. So the hypothesis might have started as a question: are parents better employees? It was not posed because hypotheses are more effective when they make a clear and forceful statement. Second, a good hypothesis suggests a relationship between variables. The hypothesis may describe the expected relationship among after-school childcare, parents' attitudes, and absentee rates. These variables might be tested to see if one, such as the enrollment in the after-school program, had an effect on the others, the absentee rate and the attitude. In what I was just saying, we want to note that it said expected. So defining an expected relationship is intended to prevent kind of a fishing trip into looking for any relationship that might be found, because that's not very productive. Third, hypotheses reflect the theory or literature on which they're based. So a lot of times we are rarely going to attribute our work just to ourselves. They're due a lot of the time in part to other researchers who came before us and laid the frameworks for other explorations that we're doing now. A good hypothesis reflects that, and it can be linked to some existing literature and theory. So let's assume that the literature indicates that parents are more comfortable knowing their children are being cared for in a structured environment, and that parents can then be more productive at work. Knowing that, it would allow us to hypothesize that an after-school program would provide the security parents are looking for. In turn, this allows them to concentrate on working rather than calling or texting to find out whether their child got home safely or not. Fourth, the hypothesis should be brief and to the point. You want it to describe the relationship between variables and to be directed and explicit as possible. The more to the point it is, the easier it will be for others to understand exactly what you're hypothesizing. and what the important variables are. A good hypothesis tells you what the general purpose of research is and how things are going to be done. Fifth, good hypotheses are testable, and testable hypotheses contain variables that can truly be measured. So this means that you can carry out the intent of your question reflected by the hypothesis. So the important comparison between parents who have enrolled their children in an after-school program and those who have not, we want to then measure things such as attitude and work days missed. And identifying those two groups of parents and measuring that attitude and absenteeism variables are reasonable objectives. Attitude may be measured by an attitude toward work survey, and absenteeism would be measured by the number of missed days at work, and it's available usually in payroll records if you're granted access to them. So how much harder would it be if our hypothesis was parents who enroll their children in after-school care feel better about their jobs? Well, it would be harder for us to define what feeling better means in a job. We need something that's measurable and easy to, not necessarily easy, but able to be measured. In hypothesis testing, there's 4 major steps. Our first step is to state the null and alternative hypotheses. The next step is to make a decision about the null hypothesis, then to draw a conclusion from the analysis, and then relate the result of the analysis to the research hypothesis, or the research question. An introduction to hypothesis testing about making a decision. So what data would convince us that the null hypothesis is false? Well, if the calculated statistic is not strong evidence, we want to look for evidence that there's a low probability occurring of the null hypothesis. What does a low probability mean? Well, an alpha level, which is symbolized as the Greek letter alpha, is the probability of the statistic used to make the decision to reject the null hypothesis. Conventionally, this is an alpha level of 0.05, which is a 5% chance of the statistic occurring if the null hypothesis is true. Testing one sample means. Let's remember that descriptive statistics allowed us to understand the shape of a frequency distribution of numbers. Now we're moving into more inferential statistics, which allow us to evaluate how different a sample mean is from a population. So here is our first inferential statistic, and these are the assumptions for the z-test for one mean. The z-test assumptions are sample size is 30 or more, there's random sampling occurring, continuous data is captured, and we assume that it's normal. So here's our first example of a one sample mean. Students being taught with a new reading skills program are tested to see how many words they can read correctly per minute, WCPM. It is known that in the normal population, children can read with a mean of 124.81 words per minute and a standard deviation of 43.26. In a sample of 30 fourth grade children in a new program, can read with a mean of 150.35 words per minute. Does this new reading program change reading ability? Well, our first step is to state the null and alternative hypotheses. So here, the null hypothesis is that the mean is equal to 124.81, and our alternative hypothesis is that it is not equal to 124.81. Now remember, we're trying to relate our sample back to the population. That's why this is stated in terms of what the population mean is. Now we'll want to make a decision about the null hypothesis. So we'll set an alpha level, identify critical values, and state a decision rule. While we're always going to be using an alpha level of 0.05, In this case, we're going to use a two-tailed test because we have a non-directional hypothesis. So it's split into two regions. That 5% uncertainty, or 0.05 alpha level, is split into two regions at the tail end, as shown in this picture. So our levels are going to be, if it's at a p-value less than 0.05, we're going to reject the null hypothesis. If it's above 0.05, we will not reject the null hypothesis. Now on to making a decision about the null hypothesis. Well, in this case, we're using a z-score of negative 1.96 or greater than 1.96 in order to reject the null hypothesis. If it doesn't fall into that range, we reject the null hypothesis. And how do we get the negative 1.96? Well, this is a standard value for a z-score for using z's with a alpha level of 0.05 or 5%. So if you're using a z-score or a z-statistic for one mean, you're going to have an alpha level of 0.05. Your z that you're looking for in that critical region would be negative 1.96 and positive 1.96. So now we're going to calculate our statistic, the z-statistic for one mean. So our z-score formula that we used in the last module was z equals the mean x minus, or the x value minus the mean divided by the population standard deviation. Because we're now using means, we're going to modify this formula. Instead of a 1x value, we're using a mean x, so we need to modify the formula. So how do we do that? We're going to use this very similar formula, which is the mean of the sample minus the mean of the population divided by the population, the sample standard deviation, or the standard error of the sample, I'm sorry. Well, the population standard error of the mean is calculated as the standard deviation divided by the square root of the sample size. So the population standard deviation would be 43.26 from that example, and our sample size is 30. So we take the square root of 30. When we get down to that answer, we get 7.89. Next, we want to calculate the z-statistic for one mean, which is that mean that of our sample minus the population mean divided by that value for the population, the standard error of the mean, which is 7.89. When we divide that out, we get a z of equal to 3.24. Now we're going to make our decision about if we want to reject the null hypothesis. Since 3.24 is greater than 1.96, we want to reject that null hypothesis. Because when we were looking at that, our critical values, we wanted, if we were going to reject the null hypothesis, it would have to be less than negative 1.96 or greater than positive 1.96. Since 3.24 is greater than 1.96, we're going to reject the null hypothesis. Now we'll draw a conclusion. If we are rejecting a null hypothesis, we are always going to be saying that there is a significant difference. In this case, we could say that it's significantly greater because it fell on the positive end. If it was a negative 3.24, we would say is significantly lower. If we accept the null hypothesis, then we are going to say that there is no significant difference between the sample and the population. Since we rejected the null hypothesis, our conclusion would be the number of words correct per minute with a mean of 150.35 in a sample of 30 fourth grade students was significantly greater than the national normal sample, which had a mean of 124.81. Then we put a comma, our z value that we found for our sample's mean which was z equals 3.24, and then we put that our p-value was less than 0.05. Now the last step is relating this result back to our research hypothesis, which was about wondering if this program was effective. So what this study found was that teaching explicit systematic reading comprehension strategies to these fourth graders is likely to increase reading comprehension skills. There's a few factors that influence the decision about the null hypothesis. One is sample size. So the larger our sample, the greater the probability of rejecting the null hypothesis, which is shown in this little table here. So when we have a sample size of 20, we do out our math to find this t-score. We get a t-score, which is very similar to the z-score, so think of them as the same, as 3.19. Now if we have a sample of 10, we're going to have a t-score of 2.25. So this is a smaller or a lower value of that is our cutoff value for rejecting a sample's mean value. So really, the bigger our sample, the easier it is to reject the null hypothesis. Another influencing factor is the alpha level. So the larger the alpha level, the greater the likelihood of rejecting the null hypothesis. So in this image, there's critical value, the alpha level that we will be using, which is an alpha of 0.05, and then there's a critical value of an alpha of 0.10. So the alpha level of 0.10 has a bigger window of rejecting the null hypothesis. So even if our result fell at, so if our result, the z-score fell at -2, in the first example we would accept the null hypothesis that there was no difference. In the second example, we would reject the null hypothesis because if the -2 fell outside of our region that we were looking for. The last thing that influences the null hypothesis is the direction of the alternative hypothesis. So if we have a non-directional alternative hypothesis, we have two tails, and if we have a directional alternative hypothesis, then we have one tail, because we're only looking at the probability at that one end. So there's a greater likelihood of rejecting the null hypothesis if we have a directional hypothesis as opposed to if we have a non-directional hypothesis. Now let's talk about confidence intervals. So far, we've known that the population mean was for our sample comparisons, but that's not really a realistic scenario. A lot of the times researchers don't know the population mean, but are going to estimate the population mean from a sample mean. Let's say we have a sample of 36 members of a sum society, and they reported their annual salary with a mean of $56,000 approximately and a standard deviation of about 12,000. This is a point estimate, a single value that's used to estimate an unknown population parameter. So that mean is 1 point estimate. If we remember sampling error, if we drew a different sample from that society, it's unlikely we would get that exact same mean again. That's where this confidence interval falls into play. The confidence interval is a range of values that, when stated with a degree of confidence, may include the population mean. So the image here is showing that 1 point estimate value with a range of values in that purple box that might contain the population of that society's mean level of income. So population estimates are commonly constructed with 95% confidence intervals. You might also see 90% confidence interval and 99% confidence intervals. But in this class, we're going to stick to 95%. So we're going to use the z-based confidence interval formula if we have the population standard deviation and any sample size, or if we have a sample standard deviation and a number in our sample greater than or equal to 30. So this formula, which is shown on the slide of 95% CI, confidence interval, is equal to the sample mean plus or minus the confidence, or the CVZ, we'll get to that in a minute, the CVZ times the standard deviation of the sample, or the population standard deviation, depending upon the sample size, divided by the standard deviation of the sample size. So this formula gives us the confidence limits, the upper and lower limits of the confidence interval. The interpretation of this upper and lower limit, or confidence limits, these are sometimes called the LL and UL for lower limit and upper limit. This might be saying something such as, the researchers are 95% confident that the true population mean of a sample with a sample mean of whatever falls between this lower limit and this other upper limit. What does a confidence interval actually imply? Well, if we look at this picture of the normal curve, we have our mean value in the middle of the population, and then we have that mean value minus 1.96 times the standard error of the sample, and the mean plus 1.96 times the standard error of the sample. And in between those two values is 95% of the sample means will fall in that interval. Another way to think about that, a little easier way, is looking at this image where we have, again, the normal curve with the two cutoff points and then the sample ranges, sample intervals, confidence intervals. So these intervals all contain the mean except the eighth one down, I think. The eighth one down does not contain that mean. But out of all of the rest of these, only one of our intervals does not contain the mean. So that means we're like 95% sure that if we took 100 random samples out of this population, only 5 of those would fall and not include our mean value. That's what we're really talking about. Some factors that affect the size of the confidence interval of the mean is sample size. The larger our sample size, the more narrow the confidence interval. A more narrow confidence interval indicates greater precision. So if we have a sample size of 10, our confidence in our 95% confidence in estimating the range of a population that has 1,000 people in it is not going to be very short. It's going to be a wider range because we have so few people from that sample represented. As we get more and more people, so if we get 35 people out of that 1,000, or 36, I think this example of 36 people, our confidence interval gets a little more narrow because we have more people represented. If we get 300 people, our confidence interval gets even more narrow because we have 300 out of that 1,000 people represented. Another factor that affects the size of the confidence interval for the mean is the desired level of confidence. The higher our level of confidence, the wider the confidence interval is going to be. So a 99% confidence interval will be wider than a 5% confidence interval. And a 90% confidence interval is narrower than a 95% confidence interval. So why is a 90% confidence interval more narrow than a 95% confidence interval? Well, if we're 95% sure, we're leaving a little bit more on our ends to on each end for error. If we're only 90% sure, we can be a little more narrow with our guesses. So think of it this way. If you're going to say, I'm 90% sure that I'm going to go to this event tomorrow, you're leaving about a 10% chance of error. Now, if I said, okay, so tomorrow comes and you end up going to the event, cool. There's only a 10% chance of error. If I say, okay, there's a 95% chance that I'm going to go to this event tomorrow, I'm pretty confident that I'm going to be going to this event. So I need a smaller window of confidence there. This table is illustrating the effect of the level of confidence on the confidence interval with a 99% and a 90% confidence interval. So here it's using degrees of freedom and the critical value based on a table that uses the different levels of confidence to give you that critical value, or CV. And then when you calculate the confidence interval, it shows you the range. So for a 99% confidence interval, our range is about $51,000 to $62,000. If we use a 90% confidence interval, our range is 53 to 59%, or 53,000 versus almost 60,000. So 90% has a smaller window, but there's more room for error. And 99% has a larger window, but there's very few people that are going to fall outside the $51,000 to $62,000 salary range. There's 3 steps to finding confidence intervals for the sample mean. First, state the desired level of confidence. In this class, it will always be 0.05, or 95% confidence. Then we'll calculate the confidence interval and the confidence limits, and then we'll draw conclusions about the confidence interval. So here's our example. Given the sample information of a sample size of 50 and a sample mean systolic blood pressure of 120 millimeters of mercury, and we have a sample standard deviation of 14.2 millimeters of mercury. What is the 95% confidence interval around the sample mean SBP of 120? So another way to this question could be asked is, we're 95% certain that the sample's true population mean lies within what interval? So we're going to pull our formula that we showed up on the other side. So 95% CI equals the sample mean plus or minus the critical value Z times the standard deviation divided by the number in the sample. So we have, filling in the values we know right now, 120 plus or minus CVZ times the standard deviation, which was 14.2, divided by the sample size, 50, the square root of the sample size, which was the square root of 50. But we still are missing 2 values in this equation. We don't know the 95% confidence interval, and we don't know the critical value, Z. The critical value Z, this is really important, is not computed by the Z formula we learned last week. If you're asked for a 95% confidence interval, the CVZ will always be 1.96, plus or minus 1.96. If you're asked for the 99% confidence interval, the CVZ will always be 2.5. These critical values stay constant since they are not relying upon sample size. So here, let's fill in our formula more. So we have 120 plus or minus the CVZ. Since we're always going to use 95% confidence interval, we're going to use the value 1.96. We have our sample standard deviation, and we have our sample size. The next step is to calculate this out. So I separated them into the lower limit and the upper limit. You don't have to do it this way, but the more work you show me along the way in your homework, although this week you have a quiz, so it won't be as big of a show your work. But do remember on your homework assignments, if you show your work, I can give you partial credit instead of just if you give me an answer and it's wrong, I don't know how you got there. Okay, so the lower limit we calculated out is 116.06, and our upper limit is 123.94. So what does that mean? Well, it means that we're 95% confident the true population mean of a sample with a sample mean of 120 millimeters of mercury falls between 116 and 123.9 millimeters of mercury. So if we took 100 samples, 95 of them would have a mean between 116 and 123.9 for their systolic blood pressure. I know this is going to be a little bit confusing, but we're going to talk about degrees of freedom. If we have a sample with fewer than 30 individuals, we're going to use the degrees of freedom, we're going to calculate them, and then a t-table to find the appropriate critical value for that degrees of freedom. Although I'll actually be giving you the critical values because I don't want to confuse you more with the t-table, because you already had the z-table from the last module. But you will need to know how to calculate degrees of freedom for this type of example. The degrees of freedom is the number of values that are free to vary when using a sample statistic to estimate a population parameter. Okay, that's a lot of words for saying the degrees of freedom formula is equal to the sample size minus 1. Major takeaway about degrees of freedom, they're the sample size minus 1. So if I ask you to calculate the degrees of freedom, you want to take the sample size and subtract 1. That's all you have to remember about those for now. Here's our next example. We're given the sample info of sample size is equal to 16. Okay, our sample size is less than 30. We're going to have to calculate degrees of freedom. Then our sample mean is IQ is 106, and our sample standard deviation is 12.4. And we want to know the 95% confidence interval around this sample mean IQ of 106. So we're going to use that same formula we had before. The only thing that'll be different is our critical value, because our sample is under 30 individuals, is going to be different. So we fill in our formula. We have our mean value of 106 plus or minus the CVT, T because it's under 30 individuals. We only use a z-score if we have 30 or more, and this T is because we have under 30. Standard deviation was 12.4 divided by the square root of the sample size. That's all the same. Now we go to the CVT. This is obtained via that t-table after we calculate degrees of freedom. So degrees of freedom for this example is the sample size minus 1, or 16 minus 1, which comes out to 15. Since that t-table is so confusing, I'm just going to give you the appropriate critical value t's for any problems you might do with this. So if I'm giving you a critical value and the sample size is less than 30, you're almost guaranteed that you'll be calculating the degrees of freedom. So in this case, we fill in that CVT into our formula. We get 106 plus or minus 2.131 times 12.4 divided by the square root of 16. When we work this out, we get our lower limit of 99.39 and our upper limit of 112.61. So we're 95% confident that the true population mean of a sample with a sample mean IQ of 106 falls somewhere between 99.39 and 112.61.